In this video, we're going to talk about the effect on the rate constant of different conditions. And this video follows on to lots of other constants, so it's a really good one to watch. Now, the effect of temperature on rate. Increased temperature, so increases that kinetic energy, moving a lot more quickly, okay? Higher frequency of collisions. Because of those frequent collisions, there's more frequent successful collisions, and therefore more achieved activation energy. And essentially, the rate goes up. So temperature increases the rate, and hopefully you've got that from your earlier studies or from earlier videos. Now, if you take a rate equation, a simple rate equation, we just put one reactant in here, you can see if we divide that, so we divide by the reactant, we get K. So, why and what effect do we have on K of increasing temperature? Well, first of all, the rate goes up. Temperature increases the rate, but at the same time as doing that, the concentration remains exactly the same. That means the numerator is going up, but the denominator is staying exactly the same. If that's the case, K is going to increase, and the rate constant, K, is going to increase. Now, if we put this into a graph, you can see here the rate constant, and you can see the temperature in Kelvin here, and you see as the temperature in Kelvin goes up, you can see that this line is going up here. Okay, and so the rate constant is increasing with temperature. So now we're going to move on to the concentration and pressure effects on the rate constant. Now, there's no change, first of all. That's really important. There's no change. Okay, so pressure and concentration don't make any change in the rate constant. People often forget, don't forget, no change. Now, that's due to concentration or pressure. Okay, but now let's have a look at why that is. So the effect of concentration on rate. You've got a simple equation here where you're going A to B. It's a one-to-one ratio. It's the simplest way to describe this. Okay, and we've got our concentration of our reactants and our concentration of our products. Just keep it simple. So 4 moles per decimeter cubed, 2 moles per decimeter cubed. Think of it like that. Now, what happens is there's a higher frequency of collisions on this side because there's more particles. And so this side going in this direction will have a higher rate. So that moves over. And then that means that your rate is going to increase on your reactants because there's essentially more reactants colliding and those higher frequency of collisions. So if we then convert that into these equations again, you can see these equations, we've done this and then divided by the concentration again. Now let's look at what's happening to the variables here. The concentration is increasing, so this number is going up. But at the same time, the rate is increasing as well. So the rate is increasing. So therefore, what you have, if you have a kind of cancelling out effect of both of these, because one goes up and the other one goes up at the same time, which means if you change concentration down or up, so for example, if the concentration decreases, the rate will decrease. If the concentration increases, the rate will increase. They kind of both cancel each other out, and the constant remains exactly the same. So now we're moving on to the effect of pressure on the rate and therefore the rate constant. So if we look here, we've got our reactants here, which we have 4 particles here and then 2 particles there. So what happens if we increase this pressure? So first of all, we need to look at the size of the container. So the size of the container is 1 decimeter cubed. Now obviously they're in the same container, but we split them up just to make it a bit more obvious. Okay, now if we take each one of these particles and just assume they're a mole, so we can go 4 moles in 1 decimeter, and then we can go 2 moles in 1 decimeter. And then we increase the pressure. So there's 2 ways of increasing the pressure. One way is to pump more particles in, which would increase the concentration. And the other way is to reduce the size of the container. So you can see here we've reduced the size of the container by half. That means in 1 decimeter, so remember that's 4 moles per decimeter, per 1 decimeter. We now have half a decimeter with 4 moles in, so 1 full decimeter is going to have 8 moles per decimeter cubed. If we then look at that, and we can say that means 2 will be going to 4 moles per decimeter cubed. So what we've actually done is increase the concentration, and therefore the rate will increase, because you can see here's a much bigger increase here. There's an increase of 4 moles here, and there's an increase of 2 moles here. Okay, so what we've done by increasing that pressure is just going to increase that rate. If it increases that rate, that's going to affect the rate equation a bit like this. So here's your rate equation, here's rate divided by A equals K again. So what happens? Our pressure increases, so our concentration of A goes up. Our rate increases, as a result, because there's a higher frequency of collisions because the concentration's gone up. So again, that effect cancels each other out and the constant remains the same. So we're now going to go on to our final effect, which is a catalyst on the rate and therefore the rate constant. So we know that a catalyst increases the rate. It increases the rate by suggesting it, giving an alternate pathway. That alternate pathway then has a lower activation energy, and therefore you get a higher frequency of successful collisions and more that achieve that activation energy. Now, that means this number, the numerator, goes up, but the concentration remains the same. So the concentration is remains the same. So you think about it like that, that means your rate constant going to increase. So we know from this video that the pressure and concentration will make no effect, but temperature and catalysts